Welcome to lecture number 13. So, today we are going to, in fact today and the next few days we are going to continue on semiconductor or equilibrium carrier statistics in semiconductors. That means determining n in conduction band, number of electrons per unit volume in conduction band, and number of holes per unit volume in the valence band. Not only determining them, and from their nature, their behavior, consequences, etc. is what we will be discussing in next few lectures. So, essentially we are going to continue from the previous lecture. So, let us start with what we did in last lecture. We said that what is the population density? We had written the population density of the electrons right here. We had written the electrons in conduction band in energy range E and E plus dE. We wrote down that as that which is Fermi distribution, and the density of states which is of the electron states in conduction band. If so, then if we have this is the number of electrons that are in this energy range, then all we have to do is integrate it over the entire energy range of the band, EC to EC top, and we will get the number of electrons that are in the conduction band. We had followed the same logic, saying that number of holes therefore are 1 minus Fe, which is the probability of finding a hole at energy level E, and GVE was the density of states for holes in the valence band. And again, if I integrate it over the whole energy range, which is on the bottom of the band, to EV, then band edge, that means top of the valence band, then we would get our number of holes at the in the valence band. Okay, so this is where we ended last time. So what I am going to do now is I had promised last time that I will show you graphically what it means. So that is what we are going to start doing in the beginning. Now I am going to write down the expressions which we are going to plot. So let me do that first. So let us see what we have derived. We said GC is equal to, this is the density of states in the conduction band. We had derived it as 1 over 2 pi 2 m E star divided by h bar square power 3 by 2 E minus E c to power half, and this is valid for E greater than or equal to E c. And we had derived, and this Fermi Dirac function, the probability of finding an electron at energy E was 1 plus E to power E minus E f is a quantity which is the Fermi level, and then we had said that n is equal to in that case E c to E top, E c top of f of E times g of C E d E, and this is what we are going to derive. Now, what I am going to do is, I am going to do one more thing, I am going to write one more expression, and the purpose of doing this graphical integration is to prove this point. I am going to write that n will also be equal to, let me use another pen here, another color here, n would also be equal to E c to, now instead of E c top, infinity f of E, everything else remains the same, right. So now what is going on? How can I change this E c top to infinity? So there are several objections which I had raised a minute ago also, earlier also, and I am going to show there are several objections to writing these equations. One over here, use of GC as this, and also this infinity which I have just marked down. These are the two questions which I am going to answer by doing this integration or the showing you some graphical constructs of these functions. So let us start with it right now and point out to you why I am able to use this expression of GC and why this integral must go to infinity. In fact, I will give you the reason right now, but the proof will come as I start doing the plots. So what I will do is, let us plot just GC. Since I am interested in plotting GC, so let us look at this function. Let us say right here is my EC, let me plot it a little bit further here. Here is my EC, here is EV, and this is all valence band here, here is all conduction band here, but I am making a further statement that there is a top to it, there is a top here, this conduction band ends somewhere which is at EC top, then there may be another band gap, maybe there may be another band gap of EG prime, and then that is irrelevant, because all my only thing we are interested in is that electrons live up to here at 0 k, up to this energy, then there is a gap which is our band gap EG, and after that there is a conduction band, and this is the relevant band, this is the first empty band after the filled band right here. Then that there are other empty bands also, the other band gaps also in principle are irrelevant. This because you will see that all electrons live only here itself. Now, if I want to plot this quantity Gc, I want to plot this quantity Gc, then let us do that. So, here is on this axis I am going to plot Gc E, and on this axis of course is our our energy axis. So, if I plot this, then or this whole axis is the energy axis. So, you can see that Gc is defined only for E greater than Ec, below that of course it is 0. So, of course, because this is density of state in conduction band starts right from here at this point of time. So, therefore, there cannot be all these values density of states below that is 0, this is empty, there are no density of states in the band gap anyways. So, we start plotting at from this point on, it goes as square root in energy, it goes as square root of square root. So, this plot will look something like this. This I am plotting as this function, I am plotting this function here, this is what I have plotted, this is the quantity that I have just plotted, this is the quantity I have just plotted. But the objection to it was that if I look at the top of the, when you reach this energy, then obviously the density of states must become 0, because there is a band gap after that. So, I had mentioned that there must be something like this, actual density of state should be something like this, that means it goes as parabola given by this expression somewhere in the middle of the band, then it should become, then this should reduce and become 0 by the time it reaches top of the band. Yet in here, when calculating n, I am going to use this blue curve which corresponds to this expression right here. How can I do that when actually density of state goes something like this and then reduces like this? This is the first point I will have to answer graphically. I am stating to you that it will be all right if I do this, if I use this expression in this integration, yet I will get the correct value of n. That is one point I have to prove to you by when I do graphical integration. Second point I want to, and the reason you will see is, and the reason it will work out is because these energies, if you look at these energies are in order of electron volts, and this band is also, band width of the band is also several electron volts, this is also few electron volts typically. And what we will see is that as we go above EC, while this function Gc continues to increase as a square root of E, but this product will go to 0 beyond some value of EC. As you increase E, this value, this integration, this product will very quickly go to 0, because this function Fe is going to go to 0 as energy increases. As you can see here, as energy increases, this function is going to reduce. After Fermi level, it is at 0 k, it goes to 0, and even at finite temperatures after EF, this function drops off very quickly. Since this function drops off very quickly, this product will drop off, it become very small, and hence as a consequence, whether Gc was taken as this or this, it does not matter, because it is going to be multiplied by a quantity which is 0. So, whatever you take, that is the point I will make later one more time. And for the same reason, whether I integrate it from EC to E top or I integrate it from EC to infinity, it matters none, because after EC up to only few kT of energy, you will, another point I will make is that all I have to do is really few kTs is kBt, up to few kBt is all I need to integrate. This region is only this product FeGC is going to live, will have some finite value only in some few kBt at the most, and hence, and since this is electron volts, this is in electron volts, kT at room temperature is 25 millielectron volts. So, if you take 3 or 5 kBt, still it is 100 millielectron volts. You are talking about 100 millielectron volts or 0.1 electron volts, whereas this whole length is in few electron volts. What that means is that this integration lives only in a small portion of this entire in-conduction band, and hence whether you integrate this from EC to E top or the way you integrate from EC, this expression from EC to infinity, it will matter none. These are the 2 points I am going to prove. These are 2 points I am going to make. Simultaneously, let us do one more thing, let us write down expression for holes also. For that, we are going to use similarly, very similarly, GV, expression for GV we had written down was 1 by 2 pi square. I think I made an error in the first one. This should have been a square in here. 2 pi square should have been there, which I missed out. So, 2 pi square 2 mp star by h bar square 3 by 2. Now, this time EV minus E to power half, where all energies are less than EV. So, this is valid for all energies less than EV, and similarly we needed a probability function, probability of finding a hole, which was 1 minus probability of finding an electron, that was e to power E minus EF divided by kBt divided by 1 plus e to power E minus EF by kBt, which we can also write by dividing numerator and denominator by this quantity. By this quantity, we could write this again one more time as 1 plus e to power minus E minus EF by kBt. All right. So, this is the expression for 1 minus Fe, and then we had said that P was going to be equal to integrated from E V bottom to E V, and this integration of 1 minus F of E G V, and then one statement at the end I will make is, one more time I will make is, and again I am going to write it in red pen, is that P is also equal to, I am going to replace it with minus infinity this time, E V 1 minus F of E G V d E. This will lead to the same thing. And again, if I do the same exercise as here, as I have done here, I will continue now this time on the valence band side and write down, if I were to plot same way as I did earlier, that here is EC or conduction band, here is conduction band EC, and this is EC top, and then there is a band gap, this is EG. EG, remember again few electron volts, and this is EV, and now we are going to say that there is a EV bottom also, and by same token there may be another gap here, and then another band here with another gap here, EG prime, let us write it EG prime, but that does not matter. Only point is that electrons fill up all the way up to here. So, the only gap which is relevant is from where electrons jump from this point to this empty state. So, these are the only two relevant band. We call this conduction band and we call this valence band, but there may be other band gaps also below further underneath in lower energies, and remember energy is increasing this way. If I do this time and do the same thing and I ask, let us plot this on this axis GV, and energy of course increasing this way, energy increasing this way, and I take this expression and plot this expression right here, then this goes as a square root of course of energy, and up to EV for E equal to EV, the density of state is 0, right here it is 0, and then as you go down in energy, this increases as square root of half, exactly same argument as given earlier. And now we will argue again same way, that really the density of state should have become 0 here. That is, there must be something, some part of the curve for GV should be like this also, so that real GV should be going from here, from let's use something else, should have been going from here and then going like this. That's what should have been the GV, but the GV we are going to use is this solid line. It should is a solid line, in spite of the fact that the correct GV curve should have been the solid line up to here, and then this dotted line like this, which takes it to 0 again at the bottom of the band. However, by same logic, we are going to say that what we are going to say is that again this product 1 minus FEGV, and right here, and I was saying that only into few kBt, about this much, this is on order of kBt, only up to this much energy, only up to this much energy kBt, only in this energy we will see that this product lies, and it will happen though the fact that GV is being given by this curve right here, this equation is what is I plotted as solid blue line right here, but nonetheless, and I am going to use this in this integration, but because 1 minus f of E will die out very quickly as you go down in energy, and hence this product will die out, and for same reason as we talked on previous slide, this quantity, whether I use GV this expression or include the dotted line, does not matter. It does not matter, and for same token we can integrate this all the way from minus infinity to EV, from minus infinity to EV rather than EV bottom to EV. It does not matter because this product is going to be 0 deep in the energy anyways. So these are the 2 points I am going to prove to you by doing some graphical or showing you some graphically, this constructs as graphically also. So let's do this. So let's go on third slide, and I'm going to make 3 cases. So let's plot case 1, and they're very similar to each other, but some points can be made. So let's take this case 1, and let's do this, that here is therefore EC, and here is EV, and energy of course increases on this axis. This is energy axis. Now what I am going to do is, I am going to plot what quantity? I am going to plot this quantity GC, which I have already done, I have plotted right here, and I am going to plot this quantity GV, which I have already done here, but I am going to put it on this slide also, right here. So on this axis is energy, on this axis is energy, and this is E, and on this axis this time I am going to plot GC of E, and on this axis we are going to plot GV of E. We are going to put number for GV of E here and GC of E there. What do they look like? I have already plotted on the previous one, right? I will reproduce this solid blue curve disregarding this dotted portion, and I will justify that why this blue curve was solid blue curve was fine. And similarly for GV, I am going to plot this solid blue curve here for the same reason on the third slide here. So let's do that. So this is the plot of GV, whose numbers can be read on this axis, and this is plot of GC, whose number can be read on this axis, but this is a plot of GC. So this is the plot. This is the plot here, and now third one I want to plot is let's draw this again. There are 4 quantities I need to plot, so I am going to keep this all these things going here. So again, this is the energy axis. This is the energy axis. This is the energy axis. this is the energy axis, and of course, these are the ECs. These are EC, I don't know what it here. So, these are the ECs. EC's level is here, EV level is here, EC is here, EV is here. Oops. EV is here, EC is here, and just so that this is also visible, this is EV, and this point is EC, and similarly right here also. What do I want to plot here? On this axis, I am going to plot now what function? I want to plot this function, and on another plot, I am going to plot this product. So, this is my strategy. So, I want to plot this function f of E. So, let us do that. Let us plot f of E. Remember, let me just do it plot of f e right here for you. So, if I were to plot f of E remember was equal to, this was EF, if EF was here, then, and this is the energy axis, then we had said that this looks like something like this. This is 1 right here, this is the probability, and if this is the dotted line, that at some finite temperature it goes something like this. It goes something like this, and this was few kT, this was few kT of energies in which this dies out, this curve dies out. This was only this, or this was few kBT. This was only few kBT in which this thing was dying out. This was few kBT only right here. So, this was dying out. Now, I am going to plot this one where energy axis is going up and f of E is being plotted right here. So, this is what I am plotting f of E right here as f of E. So, now how would it look like? Now, we have to know where the Fermi energy is, where EF is, it all depends on EF. That sets the 3 cases. In the first case, I am going to take the Fermi energy right here, about middle of the band gap. I am going to take Fermi energy somewhere here is my Fermi energy, somewhere here is my Fermi energy. So, what happens if Fermi energy is here? Let us take this axis as, let us take this value as 1. So, this value is 1. So, this value somewhere here would be half. So, somewhere here is the point where the this function becomes half. I am plotting on this axis, I am plotting f of E. So, right here is value 1. So, what happens now? You know that this function becomes half, this becomes half, its value becomes half at EF when E is equal to EF. So, when E is equal to EF, this function will be half. So, let us just plot this, let us use this red to plot f of E, goes something like this. Isn't it? I have accelerated this picture that I am plotting the same function, that for all values less than energy less than EF, this function for values EA energy is less than EF, this function tends to 1. So, for energies less than EF going this way, this function is tending to 1 and it falls off, and I am showing you that, remember, in few kBT I said that this should fall off, and then silicon, this band gap is about 1 electron volts, this band gap is 1 electron volts, and kBT at room temperature, like I said, is 25 milli electron volts. So, I have accelerated this picture that I have shown that as if this curve is falling off fairly slowly, because this much will be 500 milli electron volts. So, within 500 milli electron volts, this curve, red curve, should have died out to 0 value very quickly, nearly 0 value very quickly. So, but I am accelerating this picture and showing you some value just for schematic, that it can be, some value can be seen on this scale. All right. So, this is what I have plotted as f of E, is what I have just plotted. This is f of E that I have plotted. Now, I want to plot also 1 minus f of E. That is simple. So, I want to plot this now. Next plot thing I want to plot is 1 minus f of E also for calculating the value of P, which is required. This 1 minus f of E is required for calculating the value of P. So, for this sake, I am going to plot 1 minus f of E also, and that is easy to plot. So, since it was 1 right here, so 1 right here, and the mirror image of f of E, it will be simply 1 minus. So, therefore, I will plot this as like this and slightly falling off, just exactly symmetrical curve. That means, if you add this, and this is a plot of 1 minus f of e. This is plot of 1 minus f of e. What I plotted here is with green line is 1 minus f of e. All right. Now, if I want to plot, now what I am going to do is, I am going to plot, next thing I am going to plot is, look at this. So, f of e and 1 minus f of e is plotted here, g c is plotted here. I am going to do what I am going to do. If you look at this, what do I need to integrate? I need to integrate this quantity. This is a quantity which needs to be integrated, product of f of e and g psi e, in order to calculate n. So, what I am going to do is plot this product. Remember, f of e was plotted by red line and g c was plotted by blue line. So, I am going to take graphically product of the red line and the blue line and then plot that. So, let us do that here, right here. So, I am going to take this g c and multiply it by f of e, which is the red curve, and I am going to plot here, therefore, f of e into f of e into g c e. That is what I am plotting on this axis right here. This is what I am plotting on this axis, on this axis. So, if I plot this, and this is product of course blue line and the red line, let us continue to use the red pen for this. What happens that for all values less than E c, which is right here, below E c, if you notice, G c is 0, and above E c, this f e function goes to 0 very quickly. So, what will happen to the product? Product will look something like this, therefore, something like this. It look like something like this. And similarly, if I plot this product of f of, if I want to plot 1 minus f of e and g v, which will be used to calculate p, then let us look how that will look like. So, we take 1 minus f e, which is the green line, and multiply with this g v curve and plot that. That I am going to plot on this axis. On this axis I am going to plot. Let me first plot it and then write the label. So, this multiply this blue curve with the green curve. Notice that for all value of energy greater than E v, this blue line is 0, and for all values less than E v going in this direction, this function falls off very quickly. So, what will happen? This curve will also look something like this, will look something very much like this. And what have I plotted here? Let me label this also. This is, on this scale I am plotting 1 minus f of e multiplied by g v of e. That is what I am plotting on this axis. So, what do I have? Now, you can see that what is this area and this area. This area is equal to n. Remember, this integration leads you to n, and similarly this particular integration leads to you to p, and hence I am going to write that this area shaded area is equal to p by same logic. Now, what you see is that, remember this function, again I go back, look at this Fe value. Fe, this band gap is in electron volts for silicon, for example, and I already mentioned that. So, this will be about 0.5 electron volts or 500 milli electron volts. This function, therefore, this red function would have dropped down very quickly, and these values will be very, very small values. So, you can clearly see that above E c, this function, this product cannot be having some finite value for anything more than few kBt. And since this conduction band is also of several electron volts, so I am very justified in using, I will be okay if I use this value of Gc, because anyway all that matters is integration from Ec to only few kBt where this product lies, after that it is 0. Hence, whether I integrate it all the way to infinity or I integrate it to conduction band top, it matters none. That is the first point I want to make. And second point is that you are free to, you are welcome to use the GC curve as, or we are welcome to use this GC curve as given by this expression right here. This is fine. Use of dotted line is not necessary. It may be possible, for example, going back to slide number 1, it may be experimentally possible to determine what EC top is, but even if I do not know it, I need to integrate only up to infinity. So, I need no knowledge of this EC top as to where EC top is, because this product goes to 0. And likewise, same argument will apply for this also. Now, what is case 2? Case 2, now I am going to draw rather quickly. What I am going to do is, I am going to notice that the way I have drawn is, when Fermi energy is in the middle, I have shown this area under red area and this green area to be approximately equal, N and P equal, and Fermi energy somewhere in the middle. You will see later when we do it quantitatively, this case will correspond to something what is called as intrinsic semiconductor. Now, what I am going to do is, I am going to take this Fermi energy very close to conduction band, and second case, in third case, I am going to take this Fermi energy very close to valence band and see how these curves look like. So, let us do that. This is case 2, and I am going to do it very quickly now, since you understand it. So, here is case 2. So, here is EC, here is EV, and here is energy axis, here is energy axis, and I am going to plot this GC, which is going to look the same way, does not matter, it does not depend where the Fermi energy is, and this is GV, this is GV. So, I am plotting this as GV, and this is GC. So, on this axis GC, on this axis GV I am plotting, and it does not depend where the Fermi energy is, but nonetheless let me mark out where the Fermi energy is. Right here is the Fermi energy. In that case, if I plot again, here is the energy scale, and I plot f of E, and here is 1 and somewhere in the half. So, if I plot this f of E, now remember Fermi energy is now here, Fermi energy is somewhere here. So, the value of f of E will be half right here. So, this f of E curve now is going to shift little bit towards the conduction band. So, it will become something like this now. This is f of E, and the 1 minus f of E will acquire half value also right here, and it will be exactly mirror image of this. So, we can plot it something like this, becoming 0 right here. So, this is 1 minus f of E when this is energy. And now, if I plot same energy scale on this, we are plotting now, this we are plotting GC and FE into GCE, and on this I want to plot 1 minus f of E into GVE. That is what I am plotting. If I do that, then this time, since this Fermi energy, this curve GC has remained the same, but f of E values have increased, because this red curve has shifted up in the energy. So, this curve this time is going to go little bit bigger than the previous case. So, I am just exaggerating this picture and showing you this, and this will be the area would be then equal to N, and this is the energy scale, and by same token 1 minus Fe would have died down more, nearly 0 it would have become, and hence this product would have become even smaller. This product would then in that case become smaller, and this area would be equal to P. Notice what happened was that as Fermi energy moves higher, this value of N is going to increase as this Fermi energy goes up, and value of P will decrease. Case 3 3 then will be, here is now case 3, last case, and I quickly plot this also then, is here EC, EC, and this is EV, and now here is the energy scale, same, I am going to plot GC and GV, and with the blue curve right here like this, they do not change with the Fermi energy, and so this is GC and this is GV, and this scale of course is energy scale, this is energy scale, and the Fermi energy we are going to this time keep it very close to the valence band edge. So, here is the Fermi energy. In that case what happens? Let us plot the Fermi energy curve. Here is the energy, this is energy, and let us do the more time right here. Here is, we are going to plot here on this, we are going to plot on this G C f of E, E C E f of E, I am going to plot 1 minus f of E into G V E. G V E is going to plot on this axis, and now Fermi energy of course is right here, sorry not here but below, Fermi energy is right here. Since Fermi energy is here, so therefore what will happen this time? This curve half Fe will become half here, so it will become really 0 and something like this. Fe, if this is 1, this is 1 and this is half, this value is half, and if I plot this is f of E, and if I plot 1 minus f of E, it will be mirror image of course of this of course. So, therefore, that will look something like should look like a mirror image, something like this. It looks something like this. This will be 1 minus f of E. So, now what happens? Because GC now compared to case number 1, GV remains the same, but the green curve has moved down. So, the 1 minus Fe value has increased. So, this part will become little bloated, this area will become little bloated, but the red one because the Fe is reduced now by shifting down, hence will become very small, something like this will come, and this area will be of course again n will give equal to n, and this area of course will be equal to P. So, what do you notice? What you notice is that few statements we can make. One, to summarize, few statements we can make that this GC value we can take as we have written our expression. The real value we need not take, real character we need not take, simply because this integration has to be carried. Is this product of Fe, GC and Fe is only in a very small energy range, few kBt, and hence we need not take, only thing we need to do is in that range value of GC should be correct, which we have ensured this should be the value. Second thing is that notice that at value of n, electrons will not live exactly at EC because density of state is 0, Genesis state is 0, but electrons live only slightly above the conduction band edge, only in the small region here, right here they live, in the small region here electrons live, only in small region here in small region here holes live, only in small region right here electrons live in this much energy, very small energies electrons and holes live. Rest of the part it does not matter, which also therefore allowed us to carry out this integration to infinity for n, and in that case up to minus infinity for calculating P. So, with this argument, these arguments, we are going to calculate these red expressions, this one for P we are going to use this, and quantitatively calculate P using this expression, and quantitatively calculate n using this expression. So, let us move forward and calculate these quantities quantitatively. So, let us move on to that step, we are going to take that step now. So, we are going to substitute all these values. So, if I do that, then I am going to write again now n. So, let us start with n now. and then same way we are going to do this for P. So, if I want to write n, now I am going to integrate only from EC to infinity. I am going to integrate up to infinity, not top of the conduction band. There is no need for it, because as you see, sorry, wrong choice of words. I will integrate from EC all the way to infinity. It makes no difference whether you integrate it to top of the conduction band or infinity. That was the logic we had used. So, let me substitute now GC. So, what is GC? 1 by 2 pi square 2 ME star by H bar square to power 3 by 2 E minus EC to power half, and we are going to also use in the Fermi function 1 minus 1 plus e to power E minus EF by KBT dE. This is the integration we need to carry out. This is the integration we carry out, and we are going to get our answer. Let us write down, let us simplify this. 1 by 2 pi square 2 M E star by H bar square to power 3 by 2 E C to infinity E minus E C to power half divided by 1 plus e to power E minus E F divided by KBT dE. This is the quantity I want to integrate. There is no analytical solution for it. So, let us use some definitions first. We are going to define a quantity called eta, which is equal to E minus EC by KBT. We are going to define this quantity. That implies d eta is equal to 1 by KBT dE. EC of course is a constant. That is the case. Then we are going to define a quantity in C as a quantity which is equal to EF minus EC by KBT. If so, now I can write n as equal to 1 over 2 pi square 2 ME star by H bar square to power 3 by 2, and if I now want to integrate it. So, now when E goes to EC, then eta goes to 0. So, I am going to write this as 0, and when E goes to infinity, then eta goes to infinity. So, this integration is up to infinity. So, now what is this quantity right here is a quantity which is equal to, in fact, so I should write this as eta to power half. E minus EC is essentially equal to KBT to power half multiplied by eta to power half. So, I should also write KBT to power half divided by 1 plus, let us see what this quantity is, E minus EF by KBT. So, if you write this as e to power eta minus eta c, then we will see what happens. Eta minus eta c is essentially equal to E minus EF. So, therefore, I will write this as 1 by, and then I am going to write this as dE. I am going to substitute as KB T d eta. So, I am going to write this as 1 by 2 pi square 2 ME star. I am going to include now KBT here, H bar square to power 3 by 2. I will take KBT out, that means 0 to infinity eta to power half divided by 1 plus e to power eta minus eta c d eta. D eta, this integration becomes like this. Now, let me introduce this Fermi direct integral of order half. as f of order half of parameter called eta c. In this case, eta c is just the parameter in there, as being quantity equal to 0 to infinity eta to power half divided by 1 plus e to power eta. So, this is a well known integral. This is a well known integral which is tabulated in many handbooks, or you can calculate this as you can calculate it numerically. So, point is that this integration does not have an analytical solution. You cannot analytically write down this integral, but we do have this as a standard. It's known as, it has a standard name called Fermi-Dirac integral of order half. So, you can use that. This Fermi-Dirac integral of order half is tabulated in many mathematical handbooks. You can use that, but now that we live in computer age, you could just carry out this integration numerically as well, and fairly simple. You could carry out this integration even on in an Excel sheet. So, so nowadays it is simple. Okay, so if that is the case, then I can write, I am going to introduce not this. It's often this Fermi function is not tabulated. Often it is common to tabulate instead a quantity called 2 by root pi, this function n c, which I have just written out. So, what I am going to do is I am going to separate out 2 over root pi. I will multiply by 2 this function by 2 over root pi and divide by this quantity by multiply. I will multiply this quantity by 2 over root pi, and I will also put a in front. I will put inverse of that, root pi by 2, that is. And if I do that, then this I can write this whole quantity n as. Okay, so so let us do that. Let us substitute all the values in there and carry on from there. So, I am going to rewrite the quantity n again. So, n now is equal to, therefore, 1 over 2 pi square 2 m e star k b t. What I am going to also do is I am going to write this as 2 pi square right here divided by h square now to power 3 by 2. That is one change I am making. Remember, h bar is equal to h bar is equal to h by 2 pi. So, this is not this h, not h bar anymore. So, it is not h bar, it is h now. And what I am going to do is what I am going to do is that I will put now a factor root pi by 2, and then also I will multiply. I am going to write this as 2 by root pi of order half now, Fermi-Dirac integral of order half. So, I am going to do a simplification of this coefficient and write the expression after that. So, what we are going to do is, in fact, carry out the simplification. So, 1 over 2 pi square, 2 pi square. What I am going to do is I am going to leave in there the quantity 2 pi square. I am going to leave 1 2 pi in there, and I am going to take out this the rest of the stuff out here from here, 2 to power 2 square root of 2, which is coming from here, and I am going to take 1 2 pi outside. So, I am going to write it 2 pi and the square root of 2 pi one more time here. I am going to write here, and therefore, I am going to write in bracket here as a quantity, and I am going to take this also right here, square root of pi divided by 2. I am doing this all multiplication, and I am going to write here now 2 pi m e star k b t by h square to power 3 by 2, 2 by 2 root pi f half ta c. So, if I carry out this, now you can clearly see that I have this 2 pi square, 1 pi is going to come from here, there is pi here. If you carry out this simplification on this, what you will find is this quantity simply becomes then 2 into 2 pi, and since I knew this answer, that is why I have just written it in a specific form, k b t, otherwise nothing is special, and it is all h now, remember, not h bar 2. That is a conventional way of writing 2 root pi. So, that is value of. So, this is what n is equal to now. This is our governing expression. Now, what I am going to do is I am going to define this quantity this quantity as, I am going to write this quantity as NC times 2 root pi f, or Fermi Dirac function eta c, where of course NC is equal to 2 into 2 pi m e star k b t by h square to power 3 by 2, and this quantity is called effective density of states in conduction band. Why this terminology will become clear in a minute, but you can see from here, not you can see, I have simplified this expression in a symbol form. NC as a standard definition, whose coefficients all this quantity is written out here. N equal to NC 2 by root pi Fermi Dirac function of order half. Having written this, let us now look at likewise let us do it for holes in the valence band also. Let us carry out the similar exercise for holes as well, and when we do for the same exercise for holes, let us go back. What I mean is, now remember we are going to carry out this integration. I am going to want to do this integration 1 minus f e multiplied by g v e. So, then I am going to substitute 1 minus f e like this and g v e like this is what we need to substitute in there. So, if we do the carry out this integration in there, let us see what happens for p. So, if you could calculate p, so now similarly if we do this p, we will get an equivalent expression, and then we will handle both these things together. In that case, I am again this time skip some steps, 1 over 2 pi square 2 m effective mass of holes by h bar square to power 3 by 2 to power 3 by 2, and now I am going to integrate from minus infinity to E v, and what I am going to integrate now 1 minus f e. So, 1 minus f e I am going to prefer to write, let us go back here. So, 1 minus f e I can also write as, instead I can write 1 minus f e 1 minus f of e as also equal to, what I am going to do is divide it, and therefore, I am going to write this as 1 by 1 plus minus of e minus E f by k b t. I can also write it like this, namely, therefore, I have basically divided by numerator and denominator by 1 by divide numerator and denominator by e to power e minus E f by k b t. So, I am going to substitute this for 1 minus f e. So, if that is so, then I will write this as E v minus e to power half. You can see the form is very similar, 1 plus e to power minus e minus E f by k b t and d e. That is integration we need to carry out. Now, if this time we are going to substitute eta as E v minus e by k b t, and we are going to substitute n v as equal to E v minus E f by k b t. We can substitute this. So, in that case, you can carry out the same exercise exactly same way which we do for n. You will find p as equal to 2 times 2 pi m p star by k b t h square, not h bar square, to power 3 by 2 . Okay, so the exactly same way, and I should in fact add this 2 to power 2 and root pi over here also, exactly same way, which we will write as n v times 2 root of pi f to power half, Fermi Dirac function of order half eta v, exactly same way. So, same form of equation where n v of course is equal to 2 pi m p effective mass of holes k b t divided by h square to power 3 by 2, which this quantity is effective density of states in valence band, of states for holes, that is obviously in valence band. So, we have an expression for P, that is what essentially this is. So, I can calculate now N and P if I can calculate Fermi direct integral, which is straightforward, that is we should be able to calculate, given that where E f is. Notice that in N V, what is the parameter? This property of material, we know where that is. So, therefore, only quantity which we need to know is, if you tell me what E f is, what the value of E f is, if you give me this is the value of E f, then I can calculate N V, and therefore, I can calculate this integral, and of course, N V is understood, that is all fundamental parameters, Planck's constant, and then of course, effective mass of holes, which comes from our EK diagram, recall that, and temperature and Boltzmann constant, etc. So, I can immediately get effective density of states. Same way for conduction band, I can calculate N c, and if you give me E f, then we can calculate Fermi direct integral of order half for N c, N subscript c. So, therefore, I can calculate N and P. Only thing I need to know is where the Fermi energy is. If you tell me where Fermi energy E f is, we are in business, we can calculate what N and P are. All right, but we are going to make some simplifications. So, this is effective density of states in valence band. So, let us move forward. So, as we continue, what we do is now try to get an estimate of approximation for this Fermi direct integral. So, that is what we are going to do now. Okay. So, if we want to do actually even before we do that, maybe let me give you some numbers. Since we can calculate this quantity N c and N v, first let us look at N c and N v. So, let us look at N c. N c was equal to 2 times 2 pi effective mass of electrons kBt to power h square 3 by 2 and V equal to 2, same expression, very similar expression, but effective mass of holes now we have to use. So, these are the effective density of states. Now, let us just calculate these numbers, how much they are. So, what we can do is, first of all, what you are going to do is simplify it. So, you know that rest mass of electron, which we are going to say m 0 is 9.11 into 10 to power minus 31 kgs, into 10 to power minus 34 joules second. So, we can substitute in there and Boltzmann constant Kb of course is equal to 8.31 divided by 6.023 into 10 to power 23. So, you can carry out this calculation, just check on this, I believe it is 1.38 into 10 to power minus 23 is what this quantity will be equal to Kb therefore. So, let us look at 300 K, what happens at 300 Kelvin, which is about room temperature, where T is equal to this is the value of T. So, T is equal to this quantity. So, what happens to Nc and Nv? Let us see what this quantity is. So, this first of all we will write this as, estimate this as, substitute all the values except Me and Mh, and then what you get. So, I am going to write this as N approximate or not approximate, I am going to simplify this expression as this quantity is equal to 2.509 into 10 to power 2226 10 to power 25 m either E or P star by m 0 to power 3 by 2, and when you calculate this you will get the answer in minus per meter cube, or therefore, I can write it as 2.509, which is more conventional is how we write it, 19 divided by 6 therefore. So, M E P star by m 0 3 by 2, and now it is in centimeters per centimeter cube. That is what density of states is. What I mean is that if you substitute in here effective mass of electrons, in that case you calculate Nc, and in case you substitute here effective mass of holes, then you calculate Nv. That is what this comma separates, pick one of the two. All right. So, that is what simplified expression is. So, if I do that, if I look at silicon for example, So, if I look at silicon, for silicon the effective mass of electrons is or divided by and with respect to with respect to the rest mass of electron. So, compared to rest mass of electron, what is the effective mass of electron in silicon? Then you find that this is equal to 1.18. That means electron is slightly heavier than the rest mass of the electron. So, and if you calculate Nc in terms of, as I said, so in centimeters minus 3, then this quantity comes out as 3.22 into 10 to the power 19 is what this quantity is equal to. And if I look at the whole effective mass for silicon, then that is 0.81 only. That means hole is lighter than hole behaves lighter in silicon than does the electron, and therefore, if I plot and I calculate Nv in units of per centimeter cube, then this number is 1.83 into 10 to the power 19. What do you see? The idea is the density of states, effective density of states is about 10 to the power 19 per centimeter cube in silicon. Remember, number of silicon atoms, however, are number of silicon atoms are 10 to the power 22 per centimeter cube. Yet, why we call it this effective density of state is, notice that this number is not 10 to the power 22 per centimeter cube, but just 10 to the power 19. Similarly, if I, and there is another reason we will see, germanium, if I write this for germanium, this is 0.55, lighter, electron is lighter, the curvature depends on curvature, remember, 1.03. in 35 into 10 to the power 18. This is in case of germanium. Now, gallium arsenide, something really very interesting happens. The electron is really light, really light, 0.066, and density of states is 4.21 into 10 to the power 17 only, whereas in relative terms between electron and holes, hole is about same heavy as, for example, in silicon and germanium. So, it is about hole in case of gallium arsenide is about same it is equally heavy as in germanium and silicon, but electron is really light, and that has a consequence in electronic devices, because electron devices therefore would be electron current can be very large, because the mass is very small. So, mobility can be very large. So, this has a very important consequence, maybe I will point out eventually as we go along little bit later, not today, but few lectures down the line. Okay, so, that gives you an idea of what the effective density of states are in these materials, 10 to the power 19, 10 to the power 17, 10 to the power 18, and here is the expression which is given to you. You can substitute in there, and you can try calculating yourself also to see if I have made any mistake, and if I have, please correct it. All right, now back to this. Nc and Nv I have estimated, Nv I have estimated, Nc I have estimated likewise. Now, let us have an estimate for this Fermi direct integral also of order half. Let us try doing that one also. So, if I do that, then what I am going to do is I want to plot 2 root pi Fermi direct integral of order half. This is the quantity I am going to plot. So, let us do that. So, if I plot this like this, here is 0 and I am plotting eta, and here is -1, here is -2, here is -3, here is -4, etc., and there is 1, 2, 3, etc., and 10 to the power -2, here is 10 to the power -1, here is on log scale 10 to the power 0, and here is 10 to the power 1. If I plot this, then at around somewhere here, so if I plot this, this looks like, this curve looks like, let me just plot from here to somewhere here, approximately I am plotting this. So, somewhere here, this looks like this curve here, a straight line is here, then in that case from 1 onwards starts behaving like this. All right. So, yeah, so maybe I plot it like this with a different pen. So, this is the plot of this red line is a plot of 2 by root pi power half eta, all right, and this black line is a plot of e to power eta. This two lines, black ones, a straight line, of course, e to power eta when taken log will become a straight line. So, that is what this plot is equal to, which I plotted here, e to power eta, that is, and then 2 power. What do we see? We see that, let us say up to here, let us be more conservative, up to here, till where all the eta values here in this direction. We can see that in this range we can find that 2 root pi eta is approximately equal to e to power eta. So, for all values of eta less than minus 3, we are going to assume that f, this function approximate to e to power eta, and therefore, we will be able to solve our problem within that those limits. I will start from next lecture on this topic, and then correspondingly I will calculate N and P in the semiconductor. Thank you.